that was not known, the composition was not known, and the arrival direction was mostly isotropic, was not known very well either. And then, as said, Agaza motivated a particle physics model to describe the origin of particles, because, as I said, there should be accelerators in the universe being located and accelerating the particles from low energies to high energies. Particle physics models, which were invented, just go the other way. They say there may be some relics from the very early universe, super heavy dark matter particles or topological defects, and they were produced at the gut scale of 10 to the 20 electron volts, and they just survived in the universe, and then if they have a lifetime of the age of the universe, they would decay these days and then cascade down into cosmic rays. And that can happen everywhere in the universe. So that basically was these kind of models. And so there were predictions made by these models, and these predictions all led to a significant flux of high energy photons and neutrinos, which we also wanted to look for. So this is then how the concept of the experiments nowadays is. This is a concept of the Auger Observatory, but also of the telescope array, a Japanese-US collaboration, and the experiment is located in Utah. So the particle enters here, cascades down, and then you observe the particles at ground with the array as I showed before. But then what's new is that at the same time we observe a light trace in the atmosphere. And the light trace is due to the charged particles exciting the nitrogen molecules in the atmosphere. And then the de-excitation is fluorescence of nitrogen, and the fluorescence light is known. You can measure again in the lab what the intensity of fluorescence light is. And then you can calculate the intensity of light, which you expect just from the charged particles in the shower. And just to give you some idea of what it is, if you take a 10 to the 20 electron volt primary particle cascading in the atmosphere here, then the intensity by the fluorescence light, which is emitted isotropically, it compares to a 60 watts light bulb, which then propagates with speed of light through the atmosphere. And that 60 watts light bulb, you can observe to distances of 30 kilometers or more, and even measure exactly what the geometry is where the light bulb moves to ground. So this is done with these telescopes here, and I should mention that actually the idea was developed in Japan a long time ago. This is indicated here. So this is the first drawing which Alan Watson and myself found in some old paper of 90. It was actually an annual report of an institute from IAMS Tokyo. And you see here's a concept. So this is indicated to be a small telescope. Here is a photomultiplier camera. The light is reflected by a mirror to the photomultiplier. And then that was, as I said, 1958. And then in 1969, the first successful observation was done by Tanahashi and his group. And so that was even before it was done in the US. But it's often forgotten. So the idea actually came from Japan. And but then it took a long time that you really could use it in standard experiments. Okay, so the largest experiment in operation is shown here. So this is the area. It's about 65 by 60 kilometers, which makes 3,000 square kilometers. And all these individual dots here, which you see, are water Cherenkov detectors to measure the particles at ground. And then you see at the periphery of the observatory buildings here, and in these buildings you find telescopes to observe the fluorescence light in the atmosphere. And they are located here, here, and there to look inside into the observatory so that you do the simultaneous observations of the particles at ground and the light in the atmosphere. That means you observe the same physical shower by two independent techniques, and that allows you to compare the results and study systematics and so on and so forth. So it's very important experimentally to have these independent observations. And so the experiment is located in Argentina. You see Buenos Aires, Santiago de Chile, and here there is a plateau of about 1,400 meter height where the observatory is located. And just to give you an impression of the 3,000 square kilometer, if you compare this to where we are now here, this is the observatory in the north of Taiwan. So it covers the northern part of the island. And so it's pretty large. So if you go there and work, I mean, sometimes you have to drive very long to get to these particle detector stations to do maintenance. There are no paved roads. I mean, you have to go through a desert-like, pampa-like Okay, so that's to give you an experience. This is how a detector looks like. You see the Andes in the background. And then what's shown here is they are filled with 12,000 liters of water. The light is read out by photomultipliers. And then the power comes from solar panels. Of course, you can put a cable there over 3,000 square kilometer. Then you want to operate detectors also at night. Therefore, we have batteries to just also survive bad weather conditions. And then there is electronics here, low power electronics, because otherwise you would have to put more solar panels here. And then you need precise timing for the reconstruction that we do by GPS. And then you communicate the data to some concentrator station, which we do actually by mobile phone technology. And so that's what this antenna is for. So that's the technique, and this is done 1,600 times. And it's really just industrial production, more or less. So this is a photograph. You see one tank in the pampa, a second tank, a third, a fourth, a fifth. So that's about already then almost 10 kilometers, which you can look here and see the tanks. So and you, in order to find them, you need to get very close by, because you see there is some grass-like nature in the pampa, and that is one of the fluorescence telescope buildings. As I say, there are 4 of these, and at night these doors open, and then the telescope look at the sky. And you can see them even by Google Maps. So this is a picture taken. It was shortly taken after the telescopes were erected, and that's the only part, at least at that time, was the only part which was measured with high resolution over Argentina. So they Google knew about the observatory, and you could even see the tanks in our backyard of the assembly area. So it was very impressive. And this is how the telescopes look like. You see here the entrance window. Astronomers here may recognize, these things here. That's a corrector, so-called correctoring, because what we are using is a Schmidt camera, which allows you to do a wide field of view without aberration effects. There's an entrance window, a UV optical filter, just to filter all the width of the starlight, and the fluorescence light is more in the UV range. This is a camera with 440 phototubes, and which is located here, and that sees the light which is reflected by this 12 square meter mirror. So in total, we operate 27 of these telescopes here. And what you see then in the telescope, this is a real event, is actually the light bulb, which I mentioned before, moving through the field of view of the telescope. And just by measuring then the light intensity, you know what the energy of the particle was. And by measuring the angular velocity, you know what the distance of the shower is, because the light bulb moves the speed of light. And then what you don't see in this figure easily is you actually measure the gradient of the angular velocity. And that gradient tells you whether the shower moves towards the telescopes or away from the telescope. Because of the changing distance, the angular velocity changes. So that's how you reconstruct the primary particles. And this is again a computer animation of a shower. And you see here the shower front now moving to ground. And here is the total number of particles. You see it increases, and then say at a height of a few kilometers it reaches the maximum. And then there's just absorption of the particles in the atmosphere, and then the number declines. And this is the light intensity profile that you observe then in these telescopes. And just by integrating the light intensity profile, you measure the energy. Here, by the way, is the central campus. Visitors are welcome. So whenever you come to Argentina, to West Argentina, pass by from Mendoza and visit the observatory, we had already almost 100,000 visitors. It's quite impressive. So many people come by. There is the famous Ruta 40, the national route, which is the longest one in Argentina when you go to Patagonia. So there are lots of globetrotters and people like this to pass by and stop. You find it also in tourist guides of Argentina. And so people come here, and then we have a visitors exhibition, and we can look at it. Okay. There's another experiment in operation, which is a telescope array experiment, very much the same, also particle detectors. In this case, these are scintillators. They are telescopes looking for the fluorescence light, and that is located in Utah, in US. And it's somewhat smaller than Auger. It has an area of 700 square meters, but apart from that, it does exactly the same physics as we do and looks at a different part of the sky. So Auger is located here, and Z is located here, and this is the declination, and you see that's the declination, the events observed by Auger, that are telescope array, and there's some overlap region here in the central part of declinations, where we observe the same sky and can compare data, which is also very important. Okay. So this is then how a shower looks like. This is footprint at ground. So these are the tanks. So you see the extension is here, say 10 kilometers, and this is a light trace which is observed by two different telescopes at a distance of, in total they are separated by 40 kilometers. And then what they observe is the profile of light intensity, which gives the energy directly. No Monte Carlo involved. It's a true measurement of the energy of the primary particle. And here you measure the particle density at ground as a function of distance from the shower core. And then what you do, that's very powerful, is you calibrate actually the ground array by the fluorescence telescopes. So here is the energy measured by the fluorescence telescopes. This is the particle density measured at ground. You see the correlation. And this correlation you can do for, say, 10% of the data, because you can operate the telescopes only in moonless nights, and which is a duty cycle of about 10%. And this 10% of data you use to calibrate the ground array, and the calibration then you can, of course, use for all data of the ground array. So it will amplify this in a sense. So you may consider the fluorescence telescopes a calibrator for the ground array, however, it's much more. Okay, so what was an important observation? So what you see here is the energy spectrum now multiplied with EQ. You see the angle here, which I mentioned before, and then there is a very steep suppression of the flux at above 10 to the 19 electron volts. And so here don't need to speak about significance. This is very significant. I mean, 7 sigmas or more by now. So the flux drops very, very sharply, and people were excited and still are excited about this. And the question now is this the famous GZK effect? That is actually the only firm prediction ever made in cosmic ray physics about the shape of the spectrum. So the question is that the effect? And of course you would say yes, because it's energy. And in the following I will try to convince you that it's unlikely the case. I mean, it still plays a role, but it may not dominate the flux suppression at the highest energies. Because what I will try to convince you is that we observe primarily the maximum energy of the extragalactic cosmic ray accelerator. So that is in fact the end of the cosmic ray spectrum, because there are no more powerful accelerators in the nearby universe. And that is then folded to be with the GZK effect. Okay, so if you compare this to the GZK effect, you in fact see with the loss in the microwave background radiation, you see that you describe that spectrum here, the experimental data with the simulations rather well. This indicates 40% systematic uncertainty on the energy scale, which agrees here with that. So you can in principle describe it by the GZK effect. You can also propagate ion nuclei that in photon disintegration and describe it equally well. So this would say yes, I mean GZK effect may be the case. However, then people came up with a different idea, and maybe it could be that you see the maximum energy of the accelerators. So the exhausting of sources, and again I remind you that the maximum energy then depends on the atomic number of the nuclei which are accelerated. So in that case you would argue that protons die out already here at 10 to the 19, and then helium takes over, nitrogen takes over, and iron then may determine the flux suppression at the highest energies. And that gives, that's a total sum here, that gives a very nice fit to the experimental data. And the question is, how would you discriminate these two models? And the easiest way is to look then actually whether the composition changes from proton-dominated here in the anchor range to a heavier composition at higher energies. So that would be the most direct discrimination. And this is done, and then the question is, how can we measure the composition? I just told you how we measure direction and energy of the particles. And the composition you measure again by this profile of light intensity in the atmosphere. And so this is one measured event at 3 times 10 to the 19 electron volt. It shows you the beauty of the data. And then if you do a simulation, so it's this curve here, yeah, the number of particles in the shower. And then if you compare this to photon simulations, you see it doesn't really compare to photons. Photons penetrate deeper into the atmosphere. If you compare it to proton primaries, then you get closer, protons fluctuate strongly, but still it's kind of shifted off from the protons. If you compare it to ion simulations, and the physics here is very basic, I don't need to discuss it, and with ion simulation it compares very well. So this in fact may be this particular event due to a heavy nucleus like ion rather than a proton, particularly not like a photon. And then when you study this in detail, you can analyze, you do this for all the air showers, and then you analyze what is as a function of the energy, the fraction of proton-like events, the fraction of helium-like events, and the fraction of nitrogen-like events and ion-like events. And then you see here a few times 10 to the 18 electron volts at the angle, the protons dominate, then helium takes over, and then nitrogen dominates at somewhat higher energies, and then there's almost no ion highest energy. So this in fact supports a picture of an increasing composition with increasing energy, and supports a picture then of seeing the maximum energy of the sources rather than GZK effect. The question is now, is this problem solved, or I mean, is this enough information? And the answer is no. I mean, this is very delicate measurements. The question is still open, but there are more independent observations which you can do to support either the one picture or the other picture. And the independent information which you have actually comes from photons and neutrinos. Just to remind you, GZK effect here, you produce a delta resonance, and the delta resonance can either decay, say here, in charged ions, and then you produce by the decay neutrinos of 10 to the 18 electron volts typically, or you do this decay into a neutral pion, and the neutral pion decays into photons, and then you get photons of 10 to the 18 electron volts just by the decay products of the delta resonance. So unavoidable. So they come automatically with the GZK effect. So you may consider this a smoking gun observation of the GZK effect. And you can also calculate very precisely what the expected flux of neutrinos and photons would be. And it would depend on whether these are protons or ion nuclei propagating through the universe. And these are the predictions here. And then when you compare this to experimental data, you see it first for the photons. So what you see here is upper limits of the photons as a function of energy. You see here a large number of models, and these were the models I mentioned before, the so-called top-down models, the particle physics motivated models for cosmic ray origin, and they are all ruled out by now. You see, I mean, the photon fluxes are dispersive, these are the upper limits, so this is allowed and this is excluded. So these models are all ruled out, which again supports the astrophysical origin of the particles rather than particle physics origin. And then you see here, this dashed line here indicates expected flux from the GZK effect. And you see we are now touching into the range of photons expected from the GZK effect, but not yet to exclude all this area. So we are just getting there. So we start to constrain at least the GZK photon. The same we can do for neutrinos. I don't explain in detail how we measure neutrinos. We do this by horizontal air showers, because neutrinos interact completely different than protons or photons in the atmosphere. And you can do the same game with neutrinos. So what's plotted here is the band here is the expected fluxes of neutrinos from the GZK effect. And the red line here is the present upper limit now from the Auger Observatory to be compared with the upper limit from the Ice Cube Observatory. And you see we constrain already strongly into the expected fluxes of the GZK effect. So if the GZK effect were responsible for the suppression, you need to see these neutrinos or photons at some point. Still, we don't exclude the entire range here, but I mean, we are now there and constraining more and more. And it would get more difficult if there were, instead of proton sources, there were ion sources. Then the fluxes would be a little bit lower like this, so we are not yet there to exclude the ion, but the protons we start to exclude. Okay. Let me talk 2 minutes about the arrival directions, since I mentioned that before. So the sky is still rather isotropic. So here's the spectrum, and then if you take all the particles above, say, 10 to the 19 electron volts, and look at the direction where these particles come from, you see here a full sky plot, and you see there is fewer particles here than there. This is the southern hemisphere. This is just, in impressive publication, and we see a small anisotropy on the scale of 4.5% amplitude. So first signatures of anisotropies, and then when you go to higher energies, here into the suppression range here, we have a nice complementary information from the telescope array here in the north, and they published last year this so-called hotspot, which has an extension of 20 degrees. So the question is there a source behind? There is no obvious source here, but there is an excess of particles. And in the southern hemisphere, this is already an older publication from Auger, 2010, where you see some excess here. It's not yet significant. In telescope array, it's 3.5 sigma. By now, I think it's even a bit more. In Auger, it's just, a 2 sigma effect, something like that. So this is just indicative, of possibly seeing the anisotropies here. And in case of Auger, there is actually a source in this direction. And that source happens to be Centaurus A, just exactly by size and position in this location. And Centaurus A, as the astronomers among you know, it's a huge object in the sky. So I compare it to the moon. You see, it has an extension of 16 degrees here. So if you would have radio skies, eyes, and look at the night sky, you would see this object in the sky like this. You would maybe be frightened by this, right? And it's simply because this object is very close by, just 3.8 megaparsec away, driven by a massive black hole here, and this is the experimental data where we see a weak excess. It's just, accidental probability by 1.5%. So it's no observation, it's just an indication. So that possibly may be related to the excess of events in the southern hemisphere, but we don't know yet. Okay. So let me come to the conclusion. What did we learn so far? Clearly we see the suppression of the flux at the highest energies. We see change towards a heavier composition towards the higher energies, which supports the maximum energy scenario over the GZK scenario. We start to constrain GZK photons and neutrinos as an independent observation of the GZK effect. If it's there, the GZK effect, and we see that the sky is very isotropic. And in fact, the 20-degree extension of the hot spot of telescope array and Auger, which we just saw, could be due to the effect if there are heavy primaries at these high energies, they are deflected stronger. So they could be easily deflected by these 20 degrees. So it's just an indication for this. So the next logical steps are that we need in the future to measure the composition towards higher energies on event-by-event basis. And what we want to do then clearly is to do anisotropy studies or look at the sky of cosmic rays selected for light primaries and heavy primaries. And that again is an independent information to tell you whether the sky looks different, and that tells you also that is heavy primaries present at the highest energies. So that is what we want to do. And as I said before, I will not have time to talk about particle physics beyond 100 TeV, so beyond, far beyond what the LHC can do. And yeah, and I think I stop at this point, and thank you for your attention.
Any questions?
You had changing composition, the top ones here. Is that one occurred after the angle, or it continues from below the 10 to 18?
It starts, let me, find it quickly. It starts actually, if I take this curve here, it actually starts to become heavier above the angle. You see, the angle is at 3 times 10 to the 18 electron volts. So I should have one picture now where you see the spectrum and the fluxes. So the change actually starts just below the angle, but basically at the angle, and then it continues to be heavier and heavier when you go to higher energies.
Okay. Actually, this is my second question is actually these pictures. Yeah. Okay. At the end, you say you want to do the composition study, but the event by event. But judging from this picture, you still can see there are so much difference.
Yes.
It's systematic difference between different kind of the interaction model.
Absolutely.
So,
Yeah.
I think it's still very, very difficult.
Yeah, absolutely. I mean, measuring the composition is the most difficult thing you can do, but that's the reason why I said we want to do this event by event, because if you see, as I mentioned briefly, if you see the sky looks different for what you think are heavy primaries and what you think are light primaries. So you don't need any model for this. You just select the group of events which, I mean, has the deepest penetration to the atmosphere and the less in the atmosphere. Whatever the interaction model would be, I mean, I don't need to know exactly whether these are protons or helium or even nitrogen. You surely know, I mean, whatever model you take, I mean, these are heavier primaries than the others. And then if the sky looks different for the one class of events compared to the other class of events, that's a very clear experimental information that there is a change of the composition and independent of the uncertainty of the harmonic interaction models. That's why we want to do event by event, exactly.
Yeah, if you want to do astronomy, you have to sacrifice all the other
absolutely.
except
Absolutely.
Yeah.
Very important point. Yeah.
Does one expect to see elements heavier than iron in cosmic rays?
I don't have that figure here now. At iron, I mean, you see elements up to uranium. However, the intensity of elements heavier than iron drops immediately by 1 or 2 orders of magnitude. So they are there, but at a flux level which is unmeasurable for us. And the reason is that iron, of course, as you know, is producing supernova remnants, and the heavier are producing supernova remnants, and only at a small amount. So they don't play a role. They are there, however, and they are measured also at low energy cosmic rays above the atmosphere.
Any further questions? Okay.
Oh. In this figure, you said the 4 elements. Have we ruled out the carbon or oxygen?
The carbon. Oh, the point here is because of, as we addressed already, there is limited resolution because the air shower is a stochastic process. You cannot measure individually, say this is a proton or this is a helium. You just can group the number of events, say in light, heavy, and something in between. And that depends on what the resolution of the experiment is, but at some point you run into the stochastic nature of the air shower. And so what we have done here, that we just subdivided it in 4 classes, and this nitrogen actually means CNO. So it's just a placeholder for CNO. And also here in helium, this also includes, I mean, the other up to carbon. And above this, the iron group is everything above CNO basically. I mean, so this is a full amount of events. Yeah, it's just 4 groups, so it bind into 4 groups. So it doesn't mean this is exactly nitrogen. So yeah, if I should have said it more clearly.
This is twice improvement.
Hmm?
Usually it only have the light and the heavy. Light is proton and heavy is iron.
So the most difficult is in fact, I mean, to separate proton from helium, because I mean, this is the most difficult with the largest stochastic fluctuations.
I have one question. So in your summary slide, you say the 100 TeV proton collider can help this cosmic ray studies. And I'm just wondering what kind of help can the collider physics provide for the cosmic ray?
Oh, it helped already. The NHE data helped already, because what we do in this is exactly the same sort of question we just discussed with the measurement of the primary mass. And to measure the primary mass of cosmic rays requires careful comparison of the experimental observation with air shower simulations. And the air shower simulations are subject to uncertainties of the hadronic interaction models, as we just said. And already now with the advent of the LHC data, the models that we use in air shower simulations were improved. Actually, I should say that when the first data arrived from LHC, particularly in the forward energy, in the forward rapidity range, that the predictions that were made by the models used in cosmic ray physics were better than the tunes of the high energy physics models. So this gave in the high energy physics community some recognition of what we do is careful work and serious work. Nevertheless, the data then were used to improve these models so that the uncertainties of the models became much less than they were before. And of course, I mean, the higher you go in energy with LHE, then